Hey everyone, Mr. Fransky here. Today we're going to talk about really 1.5. This is kind of a split between two sections, but this is about inverse relations. This is going to lead into our discussion in the last video about inverse functions. So students will be able to understand inverse relationship and the concept of undoing. So inverse functions undo each other. That's kind of the key word that I'm going to be talking about in this video. So, key vocabulary: domain, range, inverse relation, and composition of functions. And I'm going to add to that list undoing. Kind of a weird vocab word, but we're going to be talking about it a lot. So, undoing inverse functions that are undoing each other. So, let's take a look. The following are compositions f of g of x. We're going to find f of x, the outside function, and g of x, the inside function. Now, these can be a little bit tricky. Some of them are easier than others, I think. Like for sine of cosine of x, I think that one's pretty easy, right? The inside function, so we think about this as f of g of x. The inside function here is definitely going to be cosine x, right? G of x is cosine x. And the outside function, f of x, is going to be sine x. Then if you did f of g of x, that cosine goes on the inside there. That's going to be our g, and so then we do the sine of cosine of x. That makes sense. Okay. Some of them are a little trickier, though, and some of them you could actually do in different ways. So let's take a look at this. Let's take a look at this one right here. So we have x squared plus 4 squared minus 3 times x squared plus 4 plus 16. Notice I have this x squared plus 4 twice. So that looks a lot like it's going to be my inside function. That's my g of x. My g of x is x squared plus 4. So what's my f of x? What has that replaced? Well, each of those blue boxes could be an x, right? So my f of x would be x squared minus 3x plus 16. And that g has replaced the x here and replaced the x here, because that's how composition works. It replaces every x that you see. Root 5x minus 6. A couple ways I can think of to do this. I think the simplest way is to say that the inside function, g of x, is 5x minus 6. Then the f of x function is just root x. Right? So this is kind of taking composition to that next level, understanding which functions are composed here. But the g function has just replaced the x, right? Now, there are other ways you could do this, right? You could do that, let's see, f of x could be the square root of 5x. And then this is going to be tricky. So if it's going to replace that x right there, it looks like our g of x would have to be x minus 6/5, right? Because it's going to replace the x there. The 5 is going to be distributed, so you have 5x, then minus the 5s will cancel here, so you have minus 6. So a couple different ways. There are a number of ways you could do these problems. It's not really one way more right than the other. This one, I'm pretty sure I would do g of x is absolute x, and I would have f of x is ln x. Just some composition problems like that on your homework. I'm going to make sure we tried a few. All right, so for each set of functions here, let's find f of g of x and g of f of x and give the domain. Now, those might give different things, right? So let's see what happens. For the first one, let's do f of g of x first. So f of g of x, putting g inside the f function. So that's going to be the square root of x squared. Now, I think that's just x, right? And let's see what our domain is. So the first thing I do is the g function. That's the inside part. So that's x squared. Well, I'm allowed to square whatever I want. And then the result is going to be a 0 or a positive number. And I can take the square root of whatever I want, or as long as it's 0 or positive. So the outputs from x squared are all going to be square rootable, I guess would be the word I would use, right? So that means our domain is all real numbers, because I can square whatever I want, and those results will all be able to take the square root, because none of them will be negative. The other way around is kind of interesting, g of f of x. So here, I'm going to take the square root of x, and then I'm going to square it. So what do I do first this time? Well, this time, first, I take the square root. I'm only allowed to take square root of positive numbers. So my domain here is only going to be 0 to infinity, but this is still x. This is another thing that's kind of interesting to graph on Desmos if you want to. If you graph square root of x squared, it'll give you the whole line y equals x, like that, all the way in both directions. If you graph the square root of x squared, it'll only give you the positive values. Kind of cool. But interesting that both of those compositions gave me back x. Kind of cool. Let's try with this one. So if we do f of g of x, so that's going to be f of x minus 5 over 2. So we'll take that x minus 5 over 2 and replace that little tiny x with it. So we'd have 2 times x minus 5 over 2 plus 5. Looks like those 2's cancel. Ooh, and then we have x minus 5 plus 5. Those cancel too, so we have x. Noticing a theme here. Let's try g of f of x. And we'll talk about the domain. So g of f of x would be g of 2x plus 5. That 2x plus 5 is going to sit on top of the fraction, that little x's. So it's 2x plus 5 minus 5 over 2. Well, those 5's go away, and then the 2's cancel. So that's x again. Looks like these are undoing each other. Interesting. Key word. Huh. Let's see how that goes. So domain for both of these, I think, is all real numbers, because you can take any real number and multiply by 2 and add 5, or subtract 5 and divide by 2. Neither of those is going to have an issue, and so the outputs will all be able to put in the input of the other function as well. All right, so inverses. Let's kind of figure out what this is, because what just happened was like, well, one function scrambles it up, right? It subtracts 5s and divides by 2, or it squares it or square roots it, and the other function is undoing it and putting it right back to x where you started. So this is the idea of an inverse relationship, is that if you plug some value a into a relation, and the reason I'm calling it a relation and not a function is because this works for any relation. Like you could have like a circle. Like a circle is not a function, but it's a relation between x and y. So like anything that involves like y equals something with an x in it, or x equals something with a y in it, or both x and y, right? Like a square circle is x squared plus y squared equals like r squared, so it would be 9. Each of these, there's some rule that requires x and y to follow some certain rule to be able to make this equation work, but it doesn't necessarily have to be a function. So what happens is if you plug a into some kind of a relation and it pops out a value b. So it scrambles it up and it pops out a value b. So this is some relation that requires a and b to be related somehow. And then what happens is if you plug b into the inverse, so whatever this thing is that we're calling the inverse for now, well, I think it's going to pop right back out. It's going to pop back out a. So these are a special pair of relationships where if you plug a and it gets scrambled up, I don't really care what this b value is. But when I plug it back into the inverse, it's going to give me back a. That's the whole point. So if ab is on a relation has a t before the I, that's true if and only if, right? The double arrow means if and only if BA is on its inverse. Interesting. So basically what happens is the x's and y's just flip. X's and y's just flip. Just flip places. Because this is what's called often called set notation. So if you have the domain of a relation, okay, so like for square root x, this might be all positive numbers. All numbers greater than or equal to 0. Okay? And if you take some element of the domain a and a relation, it's weird to not call this f of x or a function, but it doesn't have to be a function, takes it over to the range. So here's our range. And let's say that takes from a to b. So ab, that's our thing that's on the relation, right? At some point, some ordered pair, x, y. Then the inverse does exactly the opposite. The inverse is going to take it from the range back to the domain. From the range back to the domain. So it looks like the domain and range kind of flip places. All right, so is it a function? So we're going to graph x squared and its inverse on separate axes. So we're just going to use a bunch of ordered pairs and switch them. Remember, AB goes to BA. So is the relation a function? Is its inverse a function? Well, y equals x squared. Let's graph some points we know. That's a parabola, right? I hope it is. Let's graph some points we know. We know that 0, 0 is on there. We know 1, 1 is on there, right? Because 1 squared is 1. How about 2? If I plug in 2, I should get 2 squared is 4. It's the same on the left. So we have negative 1, 1. And we have negative 2, 4. So these are points that are on the relation itself. So then the opposite, right, just BA should be on the inverse. Let's graph some of those. So 0, 0 and 0, 0 are the same, right? Because if you switch the two zeros, it's still 0, 0. 1, 1 is still going to be there. So it's like here. 1, 1. Negative 1, 1 is now going to become 1, negative 1. Oh, it looks like right away we know it's not going to be a function. So 1, negative 1, right? Because already it doesn't pass the vertical line test. Now let's see here. 2, 4 is going to become 4, 2. So this is 1, 2, 3, 4. So 4 2s, like right there. And then negative 2, 4 is going to become 4, negative 2, which is right there. So what does this look like is happening here? It looks like it's a sideways parabola, kind of, huh? Interesting. So what happened? Oftentimes when people see this, they say, well, it looks like it rotated. But really, if you think about it, what happened here is if you switch the x and the y coordinates, all of the points kind of go down this way. Right? because if I switch the x and y, basically whatever is, if it's taller, it's now going to be further out. It's going to be like longer, right? What really happens here is we're reflecting over the line y equals x. You're taking all these points, reflecting them across the line y equals x. This is a reflection over the line y equals x. So then how can we know if the relation has an inverse that is a function? So over here, right, the way we tell if something's a function is by the vertical line test. And over here, yes, it passes it. So if I want to know if its inverse is a function, that would mean that the inverse has to pass the vertical line test. In this case, it does not. Well, what does a vertical line correspond to on the original graph? Well, I think it would be a horizontal line, right? Because basically, if there's any two y coordinates that are the same, that means that the x coordinates are going to be the same on the inverse. So we're going to use what's called the horizontal line test. Now, don't get this confused with the vertical line test. The horizontal line test tells us that if a horizontal line hits 2 points, then the inverse is not going to be a function. Okay, so a vertical line test is still good to tell if this is a function itself, but then if I want to know if the inverse is going to be a function, I have to look at the horizontal line test. Cool. Okay. All right. So we're going to take a look at a few functions here, and the different functions are going to, well, they're not all going to be functions, I should say, but we're going to learn about what's called one-to-one here. So a function is 1 to 1 if it passes the horizontal and vertical line test. Passes horizontal line test and vertical line test. Okay, and basically the reason it's called 1 to 1 is because every x coordinate has exactly one y coordinate, and the other way works around too, right? So like let's graph something that's 1 to 1, like I don't know, maybe a line. Okay, for every y value that I choose, there's only one x value. That's not true for something like a parabola, right? Because if I choose a y value, there are two different x values it could have. And that's why the inverse isn't a function. A one-to-one function has to have exactly one y value for every x value and vice versa. So the way I usually do this in class is by applause. And I was like, I can't do that on a video, but I was like, sure I can. Why not? Let's give it a shot. So what we're going to do here is as I go through these different functions, there it is. As I go through these different functions, we're going to have a round of applause to see if it is a function itself and if its inverse will be a function. And I'm going to clap, and if you want to get a friend to clap along with you so you don't feel quite so silly clapping, we're going to be able to do this together. So let's take a look at the first one here. So first one we're going to graph is x cubed, something like that. So is it a function itself? Yes, it's a function itself. Round of applause. Excellent. Okay, this function feels so loved. All right, so it's a function. Wonderful. Would it inverse be a function? Well, does it pass the horizontal line test? Yes, I think it does. So round of applause for that function twice. Okay, so it's a one-to-one function, right? 1 to 1. Okay, all right, let's take a look at another one. Let's graph 1 over x. Pew, pew. There we go. All right, so is it a function itself? Does it pass the vertical line test? I think it does. Yes, absolutely. And would its inverse be a function? Does it pass the horizontal line test? Yeah, no horizontal line test passes through any 2 points, so that one gets a round of applause as well. Excellent. Okay. All right. So the next one, let's take a look at one a little bit different. We're going to do the inverse square graph, which is not a parent function we've talked about yet, but it's not too complicated. It's 1 over x squared. So is this a function? Yeah, I think it is. Absolutely, right? Because it passes the vertical line test. How about its inverse? Ooh, if we reflected this over the line y equals x, it would look like this. That would not be a function. And we can tell by seeing that it doesn't pass the horizontal line test. So if you want to boo this thing, you go ahead, right? Boo. Yeah, no, not a function. Not inverse, right? So let's take a look at the next one. I'm going to make a circle. Is that a function? Boo, I don't think so. Is its inverse a function? Nope, definitely doesn't pass the horizontal line test. That's another boo. Definitely not. All right, we're going to graph one here. We're going to look at a lot of functions like this. This is called a rational function in Chapter 2. It's got some vertical asymptotes, maybe. Is it a function? Looks like it passes the vertical line test, so yeah, absolutely, right? Round of applause, absolutely, for sure. How about its inverse? Looks like those horizontal lines are going to cross a couple times, so I'm going to give that a boo. It's not going to be, not at all. Okay, so I think that's the last slide I have, but I kind of want to say one more thing, and I'm going to add it to the last slide, so I'm going to have to go back here through all of our rounds of applause. There we go. Oh, too far. So, horizontal line test tells us if a relation has an inverse that is going to be a function. So there is some notation we can use for this, because if it's going to be a function, so if it's 1-to-1, so if the function is 1-to-1, which means it passes the horizontal line test and vertical line test, then its inverse is a function, and we call it, getting excited about the F already, we call it F inverse of x. F inverse of x. So it's F, looks like to the negative first power. That's just notation that we use for inverse functions. So we read it F inverse of x. So we don't say F to the negative first power x, we just say F inverse of x. F inverse of x. That means it undoes whatever the function itself does. Okay, and remember, if AB is on F, which means F of A would be equal to B, right? So if I plug A into the F function, it gives me B. Then BA is on F inverse of X. In other words, F inverse of the value B gives us back the A value, it returns the A. Okay? So that's what I want to talk about with inverse relations and functions in this video. We're going to talk more about how we can find inverses and how we can graph them and how we can prove inverse functions in the next video. I will see you guys there. Love you guys. That's why I'm here. Have a great day.